Okay, let's get started. Today we're going to talk about the advanced heap exploitation techniques. In fact, this is the most difficult part of the entire semester, which it involves very advanced heap exploitation technique that work in current environment as well. Before we jump to the technical content, I have some administrative trivia. Our in-class CTF schedules on December 1st. Not December 1st. And then I highly recommend you guys register as soon as possible. If you couldn't find proper team members, either talk to TA or announce in Canvas so that other people can see, or edge discussion so that other people can see your post and match each other. Okay. Surprisingly, this is the last lecture of the semester. I'm glad that many of you guys survived during the semester. This last lab is very challenging, frankly. But once you get familiar with those, it actually help you in your future career significantly. Probably if someone just take the career after graduation, never know about the details of heap allocator in general, probably didn't have any lifetime opportunity to actually learn about what it is. But it's a great opportunity that we actually digest the detailed design decision. And today, we're going to talk about the actual implementation together. Beyond the CTF event scheduled right after Thanksgiving, we also have NSF Codebreaker Challenge. It's due. It's the first week of December 8th. Probably that's the last date that we can submit our grade as well. So please work on. We at Georgia Tech actually placed on the top rank right now, but we highly recommend everyone complete it to the latest task in NSA Code Breaking Challenge as well. Right. Today we're going to talk about the large part of modern vulnerabilities. This graph shows how many CVE reported in Microsoft product over the year. If you see the top represent the stack corruption. But unfortunately, the stack corruptions almost disappear in recent years. But still, if you see large part of those vulnerabilities are related to heap corruption and related part of the heap. So if you see the bottom, the blue part, light blue, that represent the heap corruptions, this particular one. And this represent user after free. In fact, if you count more recent year, there are more vulnerability reported in user after free. This is the biggest topics in today's lecture. And also there's still some of the vulnerability in heap overflow, meaning that you can you can access to out of bound memory regions in heap objects, right? And some of vulnerability are identified as uninitialized use or type confusion. And in fact, these vulnerability also are highly relevant to the context of heap allocation. Heap vulnerabilities are considered most critical vulnerability because it enables very significant attack vectors in your software. Not only that, some of those vulnerabilities are critical and universal, meaning that even if you don't understand the application context, you can still exploit. And this exploitation just leverages the system-wise library and their metadata in process memory space, so that really you really don't need any extra help from the application logic. You can just abuse the metadata and their associated data inside the heap so that you can exploit in very reliable manner. And also, not just that there is a interesting API decision made by heap allocator, which actually are very error prone. What if we free multiple objects at the same time? What if we abuse the size parameter of the malloc? These are pretty error prone for the end user and as a developer. These are the high level interfaces that we discussed last time. We talked about malloc and free. But in fact, there are many other API associated with heap allocator. For example, if you want to allocate it with allocate some array, it's common that we invoke calloc which accept the number of elements and corresponding size, the size of each object. So that internally, it allocates large chunk sequence of memory as array. Not only that, it actually initializes so that unlike many other interfaces that just leave the memory region as it is, Kellogg actually initializes with 0. So that it's just completely safe to access those memory regions after. Sometimes we can avoid the use of the free by reallocating the same memory region. Internally, depending on the size requirement, it might free and reallocate it once more. But reallocation API just enable more efficient way to readjust the memory regions by leveraging heap allocation. When it comes to C++, there's a similar binding. For example, if you type new with the class name, it actually invoke internally allocate this malloc. Or there's actually similar implementations they rely on. Similarly, if you allocate new array in C++, they also relay this invocation to malloc. For example, if you type malloc if you type new type with the size, it basically indicates I like to allocate this sequence of array. The big question here, what if the size of the type, and because we have to allocate the sequence of the objects, we have to multiply the size parameter. What if we overflow? Previously, there are lots of interesting attack vectors associated with them. So because they simply relate those type size and number of parameters as part of their malloc invocation, now because of the security concern, recent version of most of the, I would say, C++ libraries now actually have explicit overflow check associated with it. It seems like pretty benign, but lots of loophole you can think of. For example, this is what we mostly discussed last time when we were designing heap allocator. What if we allocate the pointer, some heap objects? What if we access them? Any idea? Is it legitimate to access this memory region? Likely it contains some garbage, but in terms of implementation, we kind of have some hint about what type of garbage is there. Likely it contains some of the object's content, the contents inside the heap object, or likely the metadata, because our heap allocator leverages these free memory regions by putting some of the pointer, the data pointer between, right? These are the commonly used attack vectors we actually do. For example, if you want to bypass the ASLR in heap memory region, this is a great method that you obtain one of the heap related data pointer inside. What about we allocate with the 0 size? Does it return null, which basically meaning the error, or does it allocate actual memory? In fact, it actually allocates the memory so that you can either reallocate and so that you can actually expand more, or using this 0 size object as a pointer to indicate a unique value inside your process. There are many interesting design patterns associated with it, so that developer decide to return a legitimate pointer at the end. Yes? It indicates size 0, but you will see that how actually heap allocator use this size parameter later, but they put some of the value that indicate size is 0. But as you can see previously, the actual size of heap metadata, heap object should be bigger than 2 times of the word size, so that they can consistently leverage this free object region. Like they want to put forward and backward pointer inside when they free, so they still keep this requirement in this object. So we can consider 0 size object, but internally likely is a 2-word size. What about we put -1? What's the type of the size parameter of malloc? It's a size t, which basically means unsigned integer. If you put -1, it indicates max unsigned int, which is way beyond the malloc can handle internally, meaning that there is a POSIX requirement of the malloc that allocate the max size of integer. It's not the max size of unsigned integer. So you can basically allocate up to about 2 gigabytes in 32-bit architecture. And more or less, there's no limitations in 64-bit architecture. What about, is there any chance that malloc return null to indicate that they allocate the first virtual address memory region? Unlike we expect the pointer return null to indicate the error condition. And this particular memory region, in fact, you can use as an application if you explicitly request to the operating system in certain distribution. But for the security measure, this region cannot be allocated with for the normal non-root applications in most of the distributions like Ubuntu as a security measure. Traditionally, this memory region was exploited multiple times because, for example, if there is no dereference in the kernel memory region, as a normal application, I like to allocate this first page of the memory so that all the null dereference, instead of trapping, they can proceed with the garbage value that we can inject it in the application side. But for these regions, it's a good idea to not leveraging these memory regions in application. So when it comes to free, what about, does free return anything as to indicate the error conditions inside? There's no return value of the free. So it means that whenever you invoke free, always succeed. In other words, if you can imagine potential memory allocation might be happening inside free, but in fact, it shouldn't be the case. The entire implementation of the free should not allocate any other memory inside, even if you want to make. That's why the actual implementation Heap malloc avoid allocations of additional data. Instead, they leverage the free memory region. Otherwise, there will be circular dependencies between the heap allocator itself that if it requires additional allocations, it's kind of a weird requirement between them. So they try to avoid any other heap allocations in free. But in fact, free often allocate additional memory, which is weird in their actual implementation, which often used as attack vectors as well. What about we access the free memory region? What does it return? There are also two possibilities. It might return the metadata of the heap. It might return some of the legitimate data of other heap objects. Between these two, there's a lot of different chance that other thread in your process might override this content, or other part of the source code might invoke the allocations of the same size, then it might return the same object pointer as a result. If you invoke free with null, by convention, it ignores. It makes it programming much better, particularly when you're handling error conditions in the program. If you invoke multiple free with the same pointer, this is one of the remarkable vulnerability against the heap allocation, what we call double free. The implication of those, because you free multiple times, when you're allocating them with the same size of the object, it might return the same pointer multiple times. In other words, you can abuse this contention between these two same allocated pointer that overriding with the same time, right? What about realloc? We allocate the realloc with the pointer, with the size. What if we access the same pointer? Can we access up to the size? Because you reallocate it. In fact, there's a two different chance. If heap allocator happen to find a consecutive memory region so they can expand the usage of the pointer, then pointer might be same. If not, you always have to get the new pointer as a result. but internally it will copy the content to you so that you can keep using the same pointer, but it is not legitimate to access the same pointer because of internal condition of the heap. Similarly, if you pass the null pointer to the realloc, it actually realloc for you. So that I locate a new pointer and return. If you access the invoke the calloc, pointer contain a initialize the memory region so that it contains 0, you get 0. Even if you're just using the pointer as it is, without writing to the memory content. Right? When it comes to designing heap allocator, there are 3 goals that we want to respect. Performance is the most important goal. That's why we have a heap allocator at the first place. Memory fragmentation is another big reason we like to have the heap allocator. The memory used to be a very scarce resources. Like this require art, how to manage the existing heap, existing virtual address in the application. Think about all good day when you're running like 1 megabyte of game with the like 500 kilobytes of RAM. We have to do all these nice tricks to maximize the use of the memory. And heap allocator plays essential role when it comes to respecting this amount of requirement of the application previously. But these days we have quite a lot of memory in most of the laptop. But still, it's very important to reuse those memory regions whenever necessary. Sadly, security is the least important, but many of the implementation want to respect security as much as possible. When it comes, as far as we don't hurt the performance requirement of the heap allocator. Most easiest implementation of the heap allocator, you can just remap the invocation of malloc with mmap. We can just invoke the unmap with free, but unfortunately performance become terrible. So whether not using this interface, instead, you can keep invoking bark and without using any free invocation. Most simplest implementation that respect the performance is that we can keep increasing certain pointer by maintaining global pointer. In actual implementation heap allocator, what we call top chunk. If you can maintain this top chunk, keep allocating based on those, and if we ignore all this free, you're gonna have most performant and also most secure implementations of heap allocation. But unfortunately, we're gonna compromise that memory fragmentation issue, meaning that we are not gonna reuse any of those memory regions. So balancing these goals in heap allocation is most important goal. That's why we have so many different heap allocation implementation that we can pick and use in modern software stack. And these are the actual most popular heap allocator that you can pick, starting with the ptmalloc. ptmalloc, if you're using Ubuntu, ptmalloc is the most popular one that balance memory utilization and performance and security very well in practice. And dmalloc is the original implementation of ptmalloc, but doesn't support multi-thread, so that ptmalloc now become the most popular implementation. And other type of distributions like FreeBSD, they're using jmalloc, and tcmalloc from Google is also focused on the performance side. And there are numerous application-specific heap allocator as well, like partition alloc is the most distinctive one that allocate the object based on type, not just the size as well. And some of the high-end computer has heterogeneous memory systems that certain memory region is not uniform, meaning that there is a latency difference between the memory that exists in a different core and different socket. They respect those architectures behind, although they try to respect this sequential memory region to the application developer. So they design some of memory allocator that respect or squeeze the performance of by leveraging the hardware characteristics of the hardware, but at the same time provide a nice interface to the end user. And more recent one, particularly focusing on the security, memalloc is very popular from Microsoft, and Scudo is another popular one from LLVM. These are the heap allocator mostly focused on security as well. Internally, they have many different design decisions they're making, but in terms of binning structure and in-place metadata, and also cardinal data metadata. We're going to discuss some of their design decision today. So binning, arguably the most popular design decision that enable the lookup of the free path, so that instead of chasing entire free list, you can quickly pick the free list, free chunk based on the size. So that many of the heap allocator rely on the binning by design. And also, instead of having separate metadata, most of the old, I'll say, heap allocator prefer in-place metadata, which is pretty nice. You can avoid the extra allocations on the side. Not only that, you can squeeze everything with the same cache line in the object as well. But interestingly, in terms of in-place metadata, most recent implementation like JE malloc and partition alloc and lib umem, these are the memory allocator do not respect this in-place metadata. In other words, they're going to put entire metadata separately from the actual use of the heap allocation, right? So that sometimes it enable some of the security characteristic, meaning that if you have an overflow of the heap object, there is no way you can overflow the metadata that exists in the other side of the memory. So people might consider these design decisions for security, but we believe they pick those design decisions for better performance. So cardinal data structure, meaning that cardinal metadata means that instead of converting pointer in more, I'll say, more metadata-like data structures, you can think of like index instead of the pointer, for instance. These are the pretty good design decisions in terms of security, so that the heap allocator do not have to use those pointer as it is. Instead, they have a chance to process those data, the non-cardinal data, and convert them in a way they can leverage as a pointer. But most of the design decision is made to support cardinal metadata, meaning that heap allocator just take this pointer from the metadata regions in heap allocator and just use it as it is. So in other words, if you pick the cardinal metadata in your design of the heap allocator, attacker can simply overwrite it and leverage this data, and heap allocator will just leverage this data as it is. So if you invoke malloc in PT malloc, in fact, they're gonna allocate this memory region similar to what we explored last time. They're gonna put one size metadata on top, and it will return the pointer in the middle, but you're gonna have the enough amount of memory region that you can override usable size as a payload. But unlike what we explored last time, we put some of in-use metadata as part of the size. In fact, they avoid the use of in-use per chunk. Instead, if you think carefully enough, previous in-use and in-use metadata are equal. Instead of checking in-use, in fact, you can check the next chunk's in-use bit to indicate the in-use status of mine, right? Instead of maintaining in-use bit as part of my metadata, I'm gonna only maintain previous in-use, so that if I want to check whether my chunk is free, we're gonna go to the next chunk and check their previous in-use bit, so that it simply indicates the in-use status of my chunk, right? So they have previous in-use as a last bit in their size metadata, and there's a map which indicate whether I'm mapped or unmapped, mapped or normal size chunk, or A indicate the particular region of the heap, which is called arena. But we don't typically use the arena bits in most of the application these days. But previous in use is the most important flag that we're going to talk about today. Okay. This is actual data structure of the PT malloc. So memory chunk represent the entire heap object plus metadata. And it has two fields, previous size and size. And previous size only makes sense when the previous in use is just not indicated the use of the previous one. Previous in use is 0, meaning the previous chunk is free, and that's the moment that you can access the previous size. Otherwise, the previous chunk is used by the other objects. Other pointer is actually alive, so that it actually contains the contents of the heap object, right? Contents of the other data of the user, so that you shouldn't access the previous size, right? But whenever it's free, the previous size fields will be updated so that it makes sense to access those when the object is actually free. And size, you can always access the size field, but we're gonna encode the state fields as part of the size. What? Yes?
So check if the size exists.
Exactly.
Check 0 and
Exactly. How to chase the next chunk? Given a pointer?
size.
Exactly. You have access to the size of the chunk. You can just add up, and you're gonna have the next chunk, right? How to go to the previous chunk? In fact, if previous chunk is allocated, you cannot, right? But if previous chunk is free, you have access to the previous size, so you can go back, right? This is interesting property of the heap allocator, right? I would say interesting property of ptmalloc. Why is it possible to encode the 3 bits of the size? Yeah, they are enforcing alignment of the heap object. What if I put 15? Hey, I like to malloc 15 bytes size. They're gonna wrap around. It's a round up to the 2 words bytes, a 2-word size of your architecture, so that they always guarantee the 3 bytes is available for you. In fact, this is a pretty good idea in terms of leveraging cache line accesses, so that it increases every object contained within the cache line boundary, which is very good for performance as well. So this is the memory chunk pointer, which indicate, as you can see here, the chunk doesn't start in the middle of the payload with the size. It in fact starts with the previous size. So in other words, all these malloc chunks are overlapping in weird way, right? Because it starts with the previous size, which is the end of the previous chunk, right? They're overlapping with the 1 word. If you want to go to the next chunk, you can just add up the size, starting from the size parameter all the way down to the payload, which is a usable size plus about 1 word, right? In other words, this malloc chunk is a unit that ptmalloc is using internally, but when they're iterating this chunk, they only compute based on the malloc chunk. So if you go to the next chunk, not only you're going to add up with the usable size by plus another word size, so that malloc chunk which consistently travels across the memory region. So there are lots of important points. First, it enables immediate lookup of the size. Given a pointer, you can subtract by 1 word, you can access them. It's pretty nice. It's constant operation. Also, we can now check if the previous object is free. How can we check? Given a size, get the metadata in the least significant bit and check if it's actually 0 or not. Next object is also, we can also check next object is free or not by iterating to the next object and the next object. Because we cannot access to the previous in-user state of the next object, we have to go to the next object to check the next object is free or not. It's a little bit weird, right? You have to, in order to check the next one, you have to iterate 2 more times to check that the previous one, next chunk is free or not. But it's still possible, right? With the constant operation. Iterating to the next object is pretty easy, just addition of the size. But there's caveat that we can only iterate back to the previous object when it's free. It's allocated. There's no way you can actually you can iterate to the previous one. This is the data structure, the same data structure, but mostly for free objects. Given a malloc chunk, now this malloc chunk forward and backward now pointing to the usable memory region of the object. But it only makes sense that this current object is free. What if we access the forward and backward when object is allocated? What does it happen? It might contain the user's data. And there's an additional pointer, linked data structure that enable much quicker iterations of the same different size. So that not just having one sequence of list, there's a multiple layer that you can quickly jump to the next size object by iterating with the second linked list. But we're going to mostly focus on the forward and backward link in this lab. So this is the data structure when the object is free. So pointer still pointing to the middle of the entire malloc chunk, but the first object inside the pointer is a forward pointer. It points to the forward free objects. If you go to the backward, it points to the next free objects in certain properties between those free objects. They are likely sorted in certain region. They are literally pointing to the next object with a similar size depending on the conditions of the object. So which we're going to talk about later. Right? But another remark is that when project is free, object is free, this heap allocator will copy the size parameter at the bottom so that the next object now should be able to iterate. Not only that, it's gonna access the another bit information of the next chunk, just updating the previous in use when the object is free. You can think of it as weird that when you're freeing this particular memory chunk, it now leverages the internally free memory region. Not only that, it accesses the next chunk and update their metadata for you, right? So, yes?
If you allocate really like the size, what if you have space to store?
That's a great question. You can think about like we talk about 2 byte allocation, 2 word size allocation. In fact, if object is small, they are not actually leveraging forward, backward, and previous size at the same time. Because it's kind of tricky condition. There's a small object. There's a special binning structure called fast bin. In fact, I kind of hinted upon that for the some object with the binning structure, they only need a single list instead of doubly linked list, right? In fact, we don't need the backward pointer. Instead, given a binning structure, you can quickly pick. In fact, previous size and backward structures often share for some reason. So for those objects, in fact, they don't need this previous size. It's too complicated. In fact, for the fast binning structure, they're not actually updating the free chunk. They're just caching internally so that they kind of avoid the use of the previous size for the smaller chunk internally. So it's okay in terms of implementation. But it's kind of a loophole in the design. Any other question? Likely before, but there's a invariant they want to respect. For example, they want to sort entire free list based on the size. So that typically when they're also depending on the size of the objects and binning structure, but assume like all this when they're yeah, probably before, but doesn't have to be. Yeah, that's not the invariant that heap allocator want to respect. Doesn't matter. So given a free pointer, we still get all the benefit of the previous allocated pointer, but at the same time now we can iterate. We can go to the next chunk and forward chunk, a previous chunk and next chunk actually. So one important invariant here is that we previously talked about how consolidation works. Whenever you're free, for the physically adjacent free object, we want to merge it together, and they call consolidation. So we like to consolidate with the previous object. We like to consolidate this particular one with the next object. Because they're doing every single time, we now have a nice invariant. There will be no adjacent free objects in the heap space. Whenever you see the free, next object is guaranteed to be a allocated chunk because everything is consolidated together. So because they're doing all the time, you can kind of see whenever you dump the entire heap memory space, there is no free chunk exists at the same time. So this is a quick summary of modern heap allocation. They really want to maximize memory usage by reusing them, and they want to avoid the fragmentation by consolidating them. But at the same time, they really care about performance. Most of the operations in heap allocator in common path, it's just constant operation. Meaning that when you're doing, this is one nice property of C program or native program in general. If you build a program with Java or garbage collective based languages, the heap allocations, the object allocation, and free are jittering, meaning that you cannot kind of expect the behavior of memory allocation. But one nice thing about native application, because of this property, the memory allocation is constant most of the time, right? So that you can kind of expect the behavior of or performance of applications more consistent or more deterministic by definition. But unfortunately, we have all this nice property, but this comes with a security implication. For example, if you don't have any metadata associated within the heap memory region, overflow basically meaning that you're literally overflowing to the object next to it, right? But we now have a security implication of overriding the metadata, which hurt the invariant of the heap allocations, heap allocator. If that's the case, whenever a heap allocator just take this value with the craft pointer inside, they might be suffering from security issue, which we're going to talk about today. Right? This is common scenario. You allocated two objects with malloc. You put the size objects. You got the P1. You invoked another size object. You allocate another size object and got P2. What if the pointer one overflow? Say you override more than size object, and then you free the P1. Right? This is a condition that we're going to talk about right now. How to exploit this particular condition. Right? One chance is that you can think of the P, because we override P1, we can override the metadata of the P2, which was allocated right after mine, right? And what are the security implications? So we're going to talk about, I'll say, one of the most complex heap exploitation technique. There are lots of details in it, but if you can follow, you can understand what's going on. Again, we're going to exploit these particular conditions and allocate one object, and we overflow and just flee the same object. Okay? This is a condition that we allocated two objects at a time. We allocated P1, and we also have a P2. Because we allocated P1, we have previously in use bits of the P1 inside the P2 size regions is updated to 1, right? Because we are using the P1. And then we have overflow. In this attack, what we're going to do is that we're going to overflow up to P2's size. Basically, we have about 1 word size of overflow. Right? We are not going beyond that. Okay? For now. In the size field, what we're going to do is that instead of so previously there's a size of the P2 exists in this memory region, right? But we're going to put a negative word size. Okay? What does implicate is that when we are checking the P2 is free or not, You can think about how to check this, the in-use fields of P2. We have to iterate to the next chunk of the P2. How to iterate to the next chunk of the P2? P1. We have to take the size fields of the P2, but unfortunately it's minus. It's negative value. Although they just store in unsigned integer, when it comes to arithmetic, it becomes negative. Meaning that the pointer will now point up to the P2 region. So instead of going to the P3, if it ever exists, right, which contain the in-use bit of the P2, it now go up, right? Now the next chunk pointing in this particular location, and now this particular memory region contain the size of the P3. So if you see the bit of the P3, in this case, we can indicate Z0, which basically meaning that the P2 object is now free because of this overriding of the size. By overriding the size fields of the P2 to negative, now iterations, instead of going beyond, is going forward. In other words, by just overriding just one word size, the previous chunk, the next chunk, now pointing to the upward, which is nicely aligned with the previous size of the previous size of my data that I'm overriding, which kind of indicating the size of the next chunk, which contain the previous in-use of the P2, right? So in other words, we can make the P2 object freed by just overriding one word, right? What's the implication of this when we are freeing the P1? Because P2 is now free, is considered to be free because of overflow. Now they try to consolidate. What's the operation of consolidation? They're going to manipulate the pointer inside the free memory regions and try to unlink this P2 from the free list and try to consolidate together. And then not only we're going to override one word size, we're going to override two more words inside the P2 object. In this case, we have complete control of the forward pointer and backward pointer of the P2. Because we override the size with the negative, we now consider the P2 is free. When we are freeing P1, they're going to consolidate it together. And during the consolidation, we now enable this vulnerability into arbitrary read and write, which we're going to talk about in next slide. Right? Do you guys understand the condition? Because one word override, now we can consider the heap allocator, now consider P2 object is free, although we didn't touch anything of the previous in use of the P3, right? By simply manipulating the size object, we kind of make the heap allocator confused about how to iterate to the next chunk. Next.
How much P2 is it size that it no longer knows how to so how much?
So in this case, there is no logic that leveraging the size that you override. So this size will be aggregated back to the size of this payload, P1, later. But again, it will incur overflow and size parameter will shrink because of this arithmetic, but it really doesn't matter at the end. Because consolidation does not care about those conditions by itself. So a quick summary, by overriding just one word, you can make the heap allocator confused about the in-use states of P2, so that when we are freeing P1, now the heap allocator will try to consolidate. So in this consolidation, they're gonna remove the P2, which is not existing in the actual free list, right? But this removing operation is pretty interesting, what we call unsafe unlink. We call this type of attack as unsafe unlink, because while unlinking doubly linked list, there is an interesting security implication you can see. In fact, you actually saw some of the vulnerability in previous challenges that just contain unsafe, unlink. of the double link, right? In fact, this is one part of such operation. So this is how they do when they're unlinking one object from the double linked list. You can think of, you're going to update the pointer, the pointing to the object that you're going to unlink. Now you're going to fetch the next one and overriding the previous, the next one's next, so that you can actually detach this one from the linked list. In fact, this is how it works. You fetch the forward link by reading the pointer, and you're going to read the backward pointer, and then you're going to update the forwards backward with the my forward. And then you're going to update the next objects backward to mine's backward. This is how we actually implement in this one, right? But in this attack, we're going to abuse the first memory write. What if, because we can override the backward pointer in this picture. Think about, we are overriding this particular memory. We have complete control over this forward link and backward link with the arbitrary data. So here, because we like to abuse this guy, what if we provide the backward pointer with whatever value do you want to override, right? And then we're going to provide the forward link with the pointer that you want to override with a little bit of manipulations of the size. In this case, the backward pointer existing right after the forward pointer, you can subtract the offset of the backward pointer from the destination that you want to override. Then when they compute the forwards and backward pointer, they do simple arithmetic, right? But it offset it to the destination pointer that you want to override. Then they ended up overriding the destination address with the data that you provide as a backward pointer, right? In other words, by overriding these two values, by providing the address that you want to override and the value that you want to override to the destination, in fact, you can launch the arbitrary memory override. What's the catch in this unsafe unlink attack? What are the conditions of the value that you can override? It's not just completely arbitrary override. Any idea? What's happening here? So backward pointer, what if I want to override 1 to the destination? This one, basically the constant, and it try to override some value, this forward pointer, which we provide as a destination, minus some offset, try to override these memory regions, in this case 1, to the value, the address itself. In other words, you can only override the address, the legitimate address region to a particular memory. If you want to override non-destinations, this non-pointer value, likely program will crash after overriding the value that you want, right? This is very important constraint. So it's not just arbitrary memory write, but in fact, you can override to the memory with the value that contain a legitimate data pointer, okay? Now, how to prevent this? Any idea how to prevent this type of attack? Any idea? Don't use linked list, right? There's another way. Or you can think of many ingenious ways to prevent. But what people implemented in current ptmalloc is that instead of just taking the pointer as it is, it try to check some invariant. So instead of just trusting all the value inside the forward and backward link, we try to iterate. And because given my pointer, my forward, and what the object that my forward pointing back to should be same. The object that I'm pointing back and they're pointing forward should match each other. In other words, by simply checking this consistency between this forward and backward object, we can kind of enforce the invariant significantly. If you want to override this, you need to craft two different objects, not just overriding one value. Now, in the destination, you kind of manipulate these object regions between so that it meet this kind of checking as well. It makes attack significantly harder and complex. Not only that, we simply check whether my backward pointing to myself and forward pointing myself in their backward pointer as well. Yes? It has performance implication for sure, but this is constant operation. It requires a couple of memory lookup, additional memory lookup in their path. But it's not the crazy optimization that require high performance overhead. There's another type. It's much simpler one. So if you understand the implication of overriding forward and backward pointer, what if we have one byte null overflow? Like you fail to use a string and copy or scanf incorrectly by adjusting their size requirement. They ended up overriding just one null byte in your API. It means you're gonna override previous in use of myself. In fact, by overriding one null byte, now previously used become from 1 to 0. And what if other pointer between them, right? Think about this as string buffer. You inject your data, and then it ended overriding one byte to the next chunk. And at a certain point, next chunk will be free. And this legitimate memory region will be free, will be consolidated together with the object the system is want to free, right? In this case, because it's a string buffer that you provide the input, you have a complete control over the forward and backward pointer of the buffer. And when previously we considered the free situations of the P1, now if a system is freeing P2, now they try to consolidate and you kind of abuse this situation for unsafe run incremental, right? In other words, one benign looking null byte override, one single byte have a security implication because of the metadata associated with this, associated with the heap allocator, right? This is two techniques that we discussed today, but in the literature, there are zillions of other heap exploitation techniques based on the conditions of the shape of the heap objects and API that you can leverage. In fact, this is a previously considered art, and this is only known among the hackers community in frag articles and whatnot. In fact, our group systemized those approaches. In fact, we ended up revealing many more. This is all the star that this is a recent vulnerability technique that we discovered in our group through the research. Let's talk about user after free. Unlike the previous heap exploitation technique, leverage exploitations of the heap metadata, the user after free, unlike this previous method, leverage the API application context. So instead of just overriding the heap metadata, now you can override some of the values that matter to application. It requires, again, application-specific context to overflow, but it's pretty much easy to understand. But when it comes to complex applications like browser, these are the most common type of vulnerability you can exploit. It's called user after free. In concept, it's pretty simple. After free, there is a dangling pointer pointing to the free memory region. If you ever override them, there is a chance that you can abuse the entire integrity of the application. Let me show you some of the context. Right? This is the application context we can think of as a browser. There is document, this is DOM element, pointing to the DOM element. In this case, you can think of the body and div element inside the DOM. Right? How to implement this? It's pretty simple. We have the common parent class called element and many of the derived class like div and body, so that document can contain many of the children as element in this structure. So document contain a child as element in their member variable. And when you're implementing, when you're actually allocating document, we kind of allocate the body and div DOM element, try to propagate this pointer inside the document. In this case, we allocated document, body, and div, and then we're gonna manipulate, we're gonna store this value inside the DOM. For example, we're going to store body as an element. We're going to store inside the document child. We can store div as an element to the document of the child. So we now have a very nice the pointer you can chase between these data structures. And then what if we deallocated body? Because we deallocate, we free this body, the entire body objects were detached, but unfortunately documents still pointing to the legitimate memory regions of the body. In certain point time, if document was iterating their child and might invoke one of the functions of the child. Unfortunately, this document child wasn't updated after free, so that they don't know this particular pointer that they contain is actually free or dangled or legitimate. In this case, because they're invoking, they're accessing some of the element inside the child, there is a chance that other people override this free memory region with potentially some of the function pointer inside, which ended up incurring control flow hijacking attack. Another API misuses, one of the common misuses of heap allocator is called double free. As I said before, we allocated one memory region, simply free 2 times. You can think of the complex application logic might do free 2 times. By structural problem inside the ptmalloc, they might return the same pointer multiple times if you ended up allocating 2 different object with the same size. So we try to understand why this is happening by singing the internal data structure of the ptmalloc, namely binning. So if you deallocate, we are maintaining this binning structure that enable quick lookup of the object. It's basically looking up the free list with the constant because of this data structure. But if you free, what's going to happen is that they're going to look up the corresponding free bins and simply put it to the object, right? So if you free multiple times, the same pointer will be stored 2 times in the free link. If someone invoked the malloc, they first pop up this free object and return. And if malloc with the same size again, they're going to pop up another pointer they store in the same bin and return back. The implication of this is that because now application contain 2 different objects pointing to the same place, they there's a chance that they can violate the integrity of the data by themselves. This is a very significant vulnerability, but is there any way we can prevent this type of attack, double free attack?
Let's check.
Exactly, this is the one of the implementation that ptmalloc has. So instead of just pushing the pointer to the same bin, they can check whether this pointer exists in the bin, right? But unfortunately, you have to iterate the whole bin structures. What they did, again, security implementation should consider the performance characteristic. What they actually implement is they're only checking the top list, the first element inside the bin. If they're doing this naive double link, in fact, ptmalloc will complain that I detect the double free because they only match element exists in the top of the link. But in fact, there are tons of loophole that you can bypass. Instead of free 2 times, you can put another element between so that you can manipulate this the structures inside each bin structure so that the check can be violated. Another kind of technique is that you put these structures inside the bin. If you trigger certain condition, this entire chunk of list will be sorted at a certain point so that in fact you can also incur similar type of vulnerability. There again, the mitigation is not complete mitigation. This is simple performance focused implementation to check double list so that ptmalloc's security measure can be bypassed pretty easily. Okay, this is a simple mitigation that people implemented. Whether this particular top pointer is same as the pointer that you want to free, they simply say, hey, double free or corruption detected on the first top. But again, this one can be easily bypassed if you consider the structures of the applications and heap structure, heap allocator. So in summary, we discussed about a lot of different classes of heap-related vulnerability. Some of the very traditional one, like heap overflow, still exists in the context of heap allocation. You can, of course, you can overflow to the next heap object and override their metadata, or override their contents inside, similar to the Stack Overflow. But similar to the Stack Overflow that override the return address, which is code pointer, you can also override the heap metadata. But many of them are data pointer, unlike the return address in the Stack Overflow. But this metadata require lots of interesting logical operations inside the heap allocator, which you can lead into significant vulnerability like arbitrary read, arbitrary write, and ultimately arbitrary executions as well. It seems like it's easy to exploit, but in fact, when it comes to application, we kind of don't know the concrete layout of the stack, layout of the heap structure. It's extremely hard to understand the heap structures in deterministic way. So that in reality, it's extremely hard to override those type of vulnerability. But there are lots of mitigation in modern implementation of heap allocator that help you identify those conditions and report to you instead of being exploited. Okay, that's all for today. Please do our lab. You're going to explore some of the technique that I mentioned, and we're going to exploit very simple data structures in ptmalloc or tcache, which is a recent component they introduced in their design. But basically, instead of having the unified caching structure like bin, they're maintaining binning structure per CPU core in thread local storage region so that you can easily overflow. Previously, it doesn't have any security measure, but a lot of people, including ourselves, reported that you have to actually have the security measure. Some of the security measures apply, but you can still abuse this component. This is the weakest component in ptmalloc right now, so that you can easily exploit. Okay? Thank you, everyone. Again, this is the last lecture of the semester, and I'm going to see you, everyone, in CTF events after Thanksgiving. And thank you.